Hello students, in this module we are going to discuss about the other type of the interception detectors. We have discussed in detail about the radiometers or wideband interception detectors in the last module, and we have also seen the limitations of those radiometers. We understood that that radiometer is not a realizable solution for the practical implementation. So, we will have a quick recap here. We have seen and the functionality and the block diagram of the radiometer in the last module. We were incoming signal was first band pass filtered, which is at a center frequency f0, which is aligned with the center frequency f0 of the transmitted incoming signal, and this filter is having a bandwidth of w matched to the signal, and this output of the filter was passing through a square law detector, and then it was integrated over a selected time duration of capital T. The square law detector and this integrator basically is an integrated and dump kind of the intercept detector or intercept radiometer, we should say. Then there was a threshold comparator, and this threshold in the radiometer was pre-selected based on the noise statistics, and there was a decision finally when the output of the integrator was above the threshold. It was a decision that the signal is present, and if it is below, the decision was the negative. So, that was the typical architecture of the radiometer, and we saw that it consists of center band pass filter, three components mainly. A band pass filter is having a center frequency f0, bandwidth w, and this w will be was equal to the total frequency hopped per spectrum bandwidth WSS, we should say. A square law operator, a square law detector block with and then followed by a t second integrator. Lastly, there is a comparator, and that was actually weighs the integrator output signal against a threshold. And if the size of the T is generally dictated by the communicator's message duration Tm. So, these are all the parameters that we have already learned. So, f0 will be aligned with the transmitted signal, bandwidth of this band pass filter will be aligned with the total frequency hopping per spectrum bandwidth. There will be a selection of this capital T for the integration that should be aligned with the communicator's message duration Tm. Once these all were there, we have seen that in the radiometer the signal to noise ratio, and we also saw in the radiometer that the gain bandwidth product, sorry, the bandwidth time product, the time bandwidth product, which is basically equal to the message time duration and the frequency hopping spectrum total bandwidth. It is a product of these two, and when for this product is really very large, the wideband radiometer performance can be calculated using this equation of 1.32. Also, this is an alternative equation of the signal to noise ratio that we have seen in the last module. And remember, inside this expression, whatever WSS and TM are known to us, and the parameter D is nothing but that inverse of this probability of false alarm and inverse of the difference between the probability of false alarm and the detection probability. And this 1.32, this equation, it is seen that this wideband detector's performance in terms of your signal to noise ratio, obviously it is proportional to the square root of this space spectrum total bandwidth WSS. So, the key point of understanding from this equation is that basically actually all the square law detector outputs, they are having this proportional criteria with the square root of the input bandwidth. And so, the key point is that the SNR is the signal to noise ratio sensitivity will be obtained, a greater sensitivity or greater detection possibilities can be obtained if we can effectively reduce this WSS. But remember one thing, that WSS is not under the control of the interceptor. This is a factor by means of which the communicator is spreading his own signal. So, effectively reduction of this WSS at the detector end means it can be done by dividing this WSS into equivalently some k sub bands or sub channels. So now the bandwidth of each and every channel Wk will be given by WSS divided by capital K. Now then in the each channel then forms a basis of a separate kind of the energy detector itself, and finally you are taking a overall detector performance and the based on a detection seeing the performance of the each and every detector in such sense. So this is a way of actually practically handling and improving the performance of the frequency hopping pulsed match detector. So once we actually are dividing the wider bandwidth over the subsequent sub channels, and then we are trying to devise the detectors with independent detectors over these independent sub channels, we are in the fact of a multi-channel frequency hopped pulse matched detector kind of the architecture. Let us see first the architecture of such detectors. So this was the RF input, and we have divided the whole WSS bandwidth. This is the total WSS bandwidth, and we have divided it into a 1 to k number of the channels, and hence the bandwidth of each sub channel is WSS by k, and they are having a separate energy detectors in each and every channel, and final decision algorithm is a combined decision algorithm is performed here at the end, and you are having a decision, final decision on the presence of the signal that is taken at the inside by via this decision algorithm. At the output you are getting that. So if I come back the expression and final explanation of this multi-channel frequency hopping pulse match detectors, it will be seen that if I choose now, the question is if I choose now the value of the k arbitrarily, so will it be a good choice? What will be a good choice of this k then? Our target is always to improve the detection probability, right? Improve the detectability of the detectors. So it is obvious that if you choose it arbitrarily, the value of the k will affect a lot on the performance of such detectors. That means when this k will be chosen, it is having a very good relation. It should be considered, it will be inherent with the frequency hopping cell bandwidth, which is actually WH, and the frequency hopping period TH. They will lead the performance inferior if you are not having choosing value of the k without having a knowledge of the proper knowledge of WH and TH. The effective performance of the detector will be inferior than that of a wideband radiometer. The key to superior operation over this wideband over the operation is that the individual channels must be matched to the hopping bandwidth, that means bandwidth of the WK individual channel bandwidth. The best option or ideal option is to choose it according to the hopping bandwidth, signal hopping bandwidth, and also the both in the time domain it should be also matched with the integration time of this independent detectors will be matched with the hop duration. So the finally an optimum multi-channel detector will be having NT number of the channels, and where NT is the total number of the hopping cells in WSS actually, and it will have the utilizing the likelihood ratio decision algorithm inside the decision block that we have seen earlier here in the decision algorithm. So likelihood estimators based decision algorithm is giving you the final decision for such circuit. So what are the essential elements now we have found in the earlier slide? The essential elements for such detectors are the of an energy detectors or the multi-channel energy detectors are the band pass filter, the square law detectors, the square law circuit or the blocks, and then the integrator, and followed by some scaling. Remember one thing, that channel outputs finally after summed or scaled output of each and every channel after their independent detection, they are summed up at the end of the each hop period, and then they are summed from all the NH hops in the messenger, they are multiplied and with results being compared to the threshold. Let us have a look into the detailed circuitry in the figure 3, then we will realize it. So inside each and every channel, we saw in the earlier graph that there is independent channels, and choice of those k is equal to such that we understand that the number of the channel will be equal to the number of the hops are actually there in the whole WSS. And now we are zooming inside each and every channel. What we are going to get is a band pass filter which is having a bandwidth of not WSS. Here it will be the hopping bandwidth, hopping channel bandwidth. Then it is entering into the square law device. It is having an integrator where the integration time is actually synced with the hopping time duration. Then finally you are having a decision here, and it is scaled also. And finally for each and every channel, the scaled version of this whole NT number of the channels are added up here. They are also multiplied, this added up here, and the added signal is having scaled version, and then finally there is a decision comparison going on with respect to a new threshold which is called here L. So remember, you have one threshold based detector running inside each and every channel, and finally on the top of that you are having another threshold to give you the final decision at the end. So two different thresholds K and L are actually present in the decision process of such detectors. When this NH, the hopping number of the hops are really very large, and it is possible to closely approximate the performance of such kind of the detectors at the output, considering the Gaussian statistics of course, and that performance in terms of your SNR will be given by this equation 1.34. Without that large assumption of NH and the Gaussian statistics, it will be very hard to give a closed form expression for this performance in terms of signal to noise ratio for multi-channel frequency hop detectors at the output. And remember, in this expression of the SNR, we have a quantity called D and this I0. So we will be having the expression for D. We have seen the expression for D earlier also. It is a difference between the inverse of probability of false alarm to the inverse of the probability of the detection. I0 is to the power minus 1, it is the inverse of this 0 order Bessel function for the first kind. And since we understand this number of the channels which is given by NT, it is basically the total number of the spread waveform, spread bandwidth, spread spectrum bandwidth given divided by the WH. And we also understand that the duration Tm or the message duration, it is nothing but the number of the hop duration, number of the hops present multiplied by the hop duration. And if we consider that the time bandwidth product is really equal to 1, which is as a typical for frequency hopping condition, we arrive at the fact this NT now I can write down in terms of WSS Tm by NH by substituting the values from these two. And if I now substitute the value of the NT in the equation of this 1.34, and then we can get another alternate expression for signal to noise ratio. So we have changed actually this NH, substituted the value of the NH, and now we are ending up with a new expression of signal to noise ratio. We can plot actually the signal to noise ratio as determined from this 1.32 and then to this 1.35 from here to here versus the WSS Tm, and with this different number of the hops, varying the number of the hops NT in that whole spectrum bandwidth as a parameter, we can obtain that. And once actually we are obtaining, the certain results are observed, which I have listed here. For a given amount of WSS and Tm, that is the time bandwidth product and the number of the hops that you are having, we can see that we will be there is an increase in the detectability obtained compared to the Optima multi-channel detectors. In the Optima multi-channel detectors, by using an Optima multi-channel detector compared to the wideband filters, we can quantify also the term. When actually this time bandwidth product was 8 into 10 to the power 9, and if I have 10 to the power 6 number of the hops, the optimum detector this multi-channel detector, it improves 11 by 11.1 dB with respect to your radiometer. So, once you are deploying the multi-channel concept, there is definitely a gain in the terms of the performance, and if this could be fully realized, at least there will be a 4-fold increment in the detection range, that is confirmed. If it is fully realized, why have we kept if it is fully realized? Because it depends actually the number of the hops. So, please remember, when the number of hop is 10 to the power 6, you need the 10 to the power 6 different number of the channels. Inside each and every channel, there is a channel based detection process going on. So, you can imagine now the hardware complexity that is involved in this multi-channel frequency hopped pulse matched detector, and hence actually in terms of your size, in terms of your power, in terms of the cost, actually this optimum detector is deemed unfeasible in the practice. And though we could see a very nice performance improvement, but it is again academic, it is a theoretical performance, and this detector can be theoretically designed, practically its implementability is under big question. So, we will proceed from here. We will try to get a realistic approach of this kind of the detector, and hence we enter into partial band filter bank combiners. We call it FBC or filter bank combiners, where actually the combiner figure will be like this. Instead of the main difference of this filter bank combiner compared to your optimum detector shown in the figure number 3 is that the instead of this scaling, it is having actually its own bandpass filter, the square law detector, integrator, but there was a scaling circuit here. Instead of the scaling circuit, we will introduce here the another threshold level, which is called K, and then actually which will detect basically whether there is a signal present in this channel or there is no signal present in that channel. So, output of the basically it is a logical detection. At the output you will get a presence of 0 or 1, I mean signal is present or signal is absent, and all that detection outputs will be odd here, and finally this will be over all the number of the hops that is going on, all the output of this OR gate we will be adding up. Finally, this added signal will be again compared with respect to the second level of the threshold fixed here. So, that is explained in the corresponding explanation here in this slide. Let us see once again. So, we have the same energy detector portions like the other one, and the decision in each channel relative to a threshold K, it has replaced the scaling operation. So, we have introduced this threshold K, and scaling operation is removed in the earlier optimum section. So, each channel will give you a decision circuitry. They will actually detect the presence of an or absence of any signal over the hopping duration, and they will give either a logic 1 or logic 0 at the output, as I have explained. All these logic values, they are odd over multiple hops, and the number of the OR output logic 1 state is basically getting accumulated in the over the number of the hops over the total message duration. And so, the Tm by Th is the number of the hops we understand, and finally, it is compared with the another level of the threshold, as I have shown you in the diagram. So, the advantage, basically there is definite advantage of the FBC over this optimum multi-channel situation. What is that? It is the simpler decision logic that we have implied there. So, that the cost is what actually, if you wish to detect give a logical solution, you have to implement actually the integration and the detection process in each and every channel at a higher SNR value for the same detection and probability of false alarm performance. So, the calculation of this FBCS by naught requirements cannot be found directly due to the again the non-Gaussian nature of those variables, and which is will be coupled with the FBC has two decision thresholds now k and l. So, any non-Gaussian variables, nature of the variables or will put some constraint on this decision, and calculation of this is by n0 again for the FBC performance analysis. And remember, we are having two different decision thresholds, so they will also have their own kind of the effect on the performance itself. So, it is not easy to find out a closed form expression for this performance analysis of FBC, it means, but the base performance can be found out by the computer simulation, and we could see that if the value of L at the last threshold lies somewhere between 5 and 25, depending on the values of the other parameters, of course, the value of the detection probability to be ensured, false alarm to be ensured, the time of hopping and the bandwidth of the hop. Based on all these 4 parameters, actually the L can lie in between 5 to 25, and a somewhat pessimistic performance bound for this FBC then can be obtained if I allow the L to be equal to 1 and the result being between the 1 to 2 dB higher in the SNR. But as we have told that L should vary between 5 to 25, depending upon where the L value is, your SNR requirement will go up. But for the theoretical analysis, once again, if I allow that the threshold value is equal to 1, the problem simply reduces to the determining the probability of the detection for each of those branches independently or per channel basis, basically independently. So, we have 2 parameters here. With the overall message detection, we are having the overall message detection, overall false alarm probabilities, which will be designed as PD and PFA, and then we will have the individual channel detection probability and individual channel false alarm probability for this detector. And this independent channel detection probability will be broadly approximately can be given by the total detection probability given by the number of the hops, and it can be also given further, it can be explained like this, and independent false alarm probability anyway it will come approximately by given by 1.36 b. It can be, this approximation holds good if your NH and NT they are sufficiently large, they are very large. The required signal to noise ratio in such situation when the NT and NH are really very large, we can develop the equation of some relation can be developed like this, equation 1.37, where this DI, the independent channel D values, that is the difference between the false alarm independent channel false alarm probability difference between the inverse Q function of independent channel false alarm probability and the detection probability. Remember this chi, the introduction of this new parameter in the expression, this is a chi-square correlation factor applied to this Gaussian assumed DI of 1.37. When we are assuming Gaussian, this is a correction factor we can call off. So, returning now again to the continuing example, where we thought that we have a detection probability of 0.9 and false alarm probability of 10 to the power minus 6. Then with L equal to 1, where are we? Let us revisit. So, FBC performance, as we have seen, we will be given by the S by N0 is like this, with the DI value is like this. So, it will be relative to the optimum multi-channel detector, the improvement actually it will be around, not the improvement, it will be a 3.2 dB worse performance when your WSSTM will be 8 into 10 to the power 9 and NT is having their same 10 to the power 6. So, comparison is such that this is the performance of this optimum detector and this is the FBC, and if I am trying to calculate the performances of both this, and if we try to compare with both of them, when WSSTM is having 18 to 10 to the power 9 and NT equal to 10 to the power 6, we will see that filter bank combiner detector has a simple circuit, simple circuit and simple implementability, but there is a loss on the performance of around 3.2 dB when my L value is definitely equal to 1. And if I increase this or decrease this NT value, if I decrease this value to 10 to the power 5 and increase this value to 10 to the power 7, then this performance gap will be visible as 5.1 dB and 2.8 dB itself. So, that is the kind of the pictures, the kind of the typical values I have given here to get an assumption that when we are entering into FBC, from the optimal performance, how far actually our performance will vary. Definitely when my NT value will be keeping on increasing, this difference will be lowered down. So, the partial band filter FBC, the partial band filter bank combiner, which is the last structure of detector structure in this series, which further tries to simplify the whole structure of this optimal filter design, optimal detector design. Partial band FBC is simply, it is an FBC, but it does not actually take care of all the channel decision outputs. It is less than the optimum or maximum number of the channels available. It deals with always. Suppose the total number of the channels we saw, it is NT, and partial band FBC deal with the number of the channels in dashed T. If it is using like that, then we can define here channel reduction factor F, which will be given by N dash T by NT. So, we will see actually all the detection probability and false alarm probability for this PB FBC now is coming a factor of this small f. And when all these NT channels are implemented, a hop frequency must appear at any one of those channels, but in case of your PB FBC, there is a probability that you will, when a chance is when the NT dash channels are employed, on a per hop basis, there may be a probability that you may capture the particular hop signal or you may not, depending on the fact whether this channel is actually designed for that hop or not. So, some of the hop channels you are definitely going to miss, and part of the hop channels you are going to get. So, there is a probabilistic matter always added to this PB FBC. When actually one signal is present with one of those channels, NT dashed channels, we call the condition that there is a hit, and the probability that there will be a hit, assuming that at least one of these NT possible hop frequencies may be there, equal to with equal likelihood, when all the NT channels are coming with NT possible hops are with the equal likelihood, then the transmitted one it will be transmitted on, and given the hop interval is, then the probability of hit will be given equal to your that f itself. On the view of this expression, so now the performance penalty we will have to pay. So, the penalty we will try to consider the penalty paid on the per channel detection probabilities PDI and PFAI. If the transmitted message is sufficiently long, then we can show that the effective per hop detection probability will be given for this FBP, your partial band FBC will be given by the PDI multiplied by hit. So, this is the performance of the detection per channel for your partial band FBC, which is actually now a function of the hit probability of the hit and the actual detection probability of per channel of FBC. So, now this is the relation between partial band FBC to the actual FBC detection probability on the per channel basis. We will see the similar expressions for the, we can find out the similar expression for the false alarm also. And so, there will be, we saw earlier that for the FBC the PDI and PFAI are looking like this. So, newly the PD dashed and PFA dashed, which are the detection probability of your complete PB FBC at the end actually will be given by this, and total probability of, it is not the part channel, it is the total probability of the detection, total probability of the false alarm at the end of the decision, means after L actually whatever is coming out will be given by this equation. And as we understand that P heat is equal to AF. So, fundamentally the total detection probability of your partial band FBC will be actually the multiplied will be actually the detection probability of your FBC multiplied by the factor f. Similar expression you can be able to find out for P dashed FA, and basically it is as a value of f is a reduction factor, it is less than 1, the value is about. So, you will always get a reduced detection probability for your partial band FBC. So, you have more and more you make the circuitry simplify your circuitry, the more the payment will be, the loss will be over the performance of the detector. Now, there are only two ways to restore the desired performance. So, we have understood already that there is a loss in the performance. So, there are two ways. Either you increase the part channel PDI and PFI by the values of 1 by f, which requires a high SNR relative to the full band FBC, or you increase the NH by 1 by f. But remember, how can you increase the NH? This is not the detector possibility, it is beyond the capacity of the detector design. So, this is fixed always by the communicator's message, you have no control over that. So, you cannot actually, so this latter one, the fixing this value may not be actually possible for you. You have no control over the message duration. So, increasing this NH is not be feasible. And the use of then FBFBC, PBFBC should be predicted on the case that it can be given, its performance can be improved then by increasing or using the larger value of S by N0 requirements. So, for a very short message to keep this requirement itself is a problem. You should understand that limitation of PBFBC. And finally, where we are coming is now we understand that the detection probability here is a factor of the probability of hit. If I consider that there are number of the hits given by small n, then and this probability of this hit will be given by this binomial distribution. So, now we can redefine the total detection probability given that value n as the expression 1.40, and now the total detection probability, if this is the distribution also added with the detection probability, the total detection probability will be PDN multiplied by the PN, definitely going by the equation of my probability of detection. And this evaluation of this 1.41 equation, finally it cannot be easily calculated again. So, but with higher value of NH, and I mean when the hopping will be very large, number of the hops are very large, and your false alarm actually probability part channel is very small, then you can approximate this PD will be approximated with this distribution of this PD n bar, and this n bar is basically the mean of this distribution given in the equation, and this mean will be computed by this NH into f. So, finally, where are you? So, finally, when my n bar is equal to NH into f and the detection probability was given by this. So, substituting this value of n bar inside this expression itself and ignoring this false alarm probability, because we have talked about that the false alarm probability is very low in that situation. If all that happens, I mean n is coming to n bar and false alarm probability is also very less. If I substitute the value of n bar inside this equation, I will be ending up with the detection probability given by 1.44. And correspondingly, this detection probability of individual channel will be given by the expression 1.45. The companion relationship for your P star FAI is can be determined from this P star DI also. So, now finally, when your partial band FBC is there, so you are not going to identify the detection probability by the original one, considering that the NH is very high. So, we can go ahead with the equation of detection probability of equation 1.44, where the detection probability independently individual channel detection probability will be given by 1.45 and its corresponding false alarm probability will be given by 1.46. We end here the discussion about the different interception filter design, and we hope that the detector possibilities and the design criteria, their limitations, that is well understood now. And so once actually somebody will try to design some interception detector, and the jammer detectors for jam detections, not only the detections, it is detection is intended for the jamming activity. So this will be the guidelines for the design of those detectors and presence of all that. On the other side, we can design such detectors inside the receiver, intended receiver also, which will help us to find out actually the presence of any other jammers that are trying to jam our circuits. And sometimes actually we can also falsely jam the jammers itself or the interceptors itself, and to confuse them about the kind of the communication actually going on.